All good. Thank you very much. Yeah, so today I'm going to talk about what controls the PGE content of porphyry copper deposits, perhaps unusually for a nickel symposium. And so porphyry deposits are mainly mined for copper and also molybdenum, but they also have byproducts, most notably gold, but also potential byproducts such as tellurium, selenium, bismuth, and potentially palladium and platinum. And all of these byproducts are chalcophile elements. And so this talk is kind of summarizing some of the research I did as part of my PhD and in my last postdoc, which was looking at critical metal sources. And really the sort of driving research question for me there was what controls why some deposits are endowed in chalcophile elements and others aren't. Now this is a huge topic, so today I'm going to focus on tectonic control and particularly whether we can predict from the tectonic setting of a porphyry copper deposit whether it will be PGE enriched or not, and what the effect of tectonic control is on that, and if it is indeed a control at all. And this has sort of been looked at over the years, and I'm particularly going to focus on the model proposed by Jeremy Richards, who sadly passed away last year, in his geology paper in 2009. Porphyry copper deposits were traditionally thought to be formed in subduction settings, but then with the advances in dating, we now know that an awful lot of them are formed in post-subduction settings. And so in subduction settings, the source of metals is the partial melting of the hydrated mantle wedge and also dehydration of the downgoing oceanic slab. And what Jeremy Richards sort of synthesized and what lots of people have done work on is that actually during this process, during subduction, residual sulfides are commonly formed. And these have a very high R number because there's a very small amount of them. And so it's been proposed that these would partition gold and one would assume PGE and other highly chalcophile elements from the source melt for these subduction related porphyry copper deposits. And so you would end up with subduction related deposits that are relatively depleted in highly chalcophile elements such as gold and PGE, and more enriched in things like copper, which have a less high partition coefficient between silicate and sulfide melts. Conversely, post-subduction porphyry deposits, their source of metals is in the remelting of previously subduction modified subcontinental lithosphere, and particularly in the remelting of those residual sulfides that are being made in our subduction system. And so these are our high R number, very chalcophile enriched sulfides. And so what should happen is that these are melted or partially melted to form the source of metals for our subduction related post-subduction related porphyries. And so these porphyries should be more chalcophile enriched relative to subduction related porphyries. And this is a very elegant theory, so it's a very nice model, but I wanted to test whether that was actually the case or not. And so to do that, we focused on 3 example porphyries. So the El Teniente porphyry deposit in Chile, which is a subduction-related copper moly deposit, the Skouries deposit in Greece, which is a copper-gold post-subduction deposit that's famous for being enriched in PGEs, and the Maratra copper-gold moly porphyry deposit in Turkey, which is post-subduction but is not enriched in PGEs. So we did laser ablation on sulfides from these deposits. We did whole rock analysis, including nickel sulfide fire assay to get the full PGE suite. And I also compiled a database of all of the trace element data for sulfides I could find from porphyry copper deposits, and then separated that by tectonic setting in order to do statistics to see if there are any systematic differences there. And also compiled all of the full suite PGE analyses I could find in the literature from mineralized samples from porphyry copper deposits. And while I was compiling the PGE enriched porphyry sort of data, so this is a paper, this is a table from a paper we published in 2018, just summarizing the main features of PGE enriched porphyries. And I should say at this point that in the porphyry world, when we say PGE enriched, we mean like 1 part per million palladium and platinum in whole rock, or else that we have identified platinum group minerals in the ore. So we're not talking about the Merensky Reef here. And we can argue over whether this can ever be economic at another point. But what I wanted to show is that all of these porphyries have been suggested in one paper or another as being PGE enriched. And if we look at that tectonic setting, we can already see that many of them are subduction related. There is a big variation here. They also have a wide variety of metal endowments. And I don't have time to go into the link between alkaline volcanism, magmatism, and PGEs in this talk, but I'd like to point out as well that they're not actually all alkaline systems. A lot of them are calc-alkaline systems as well. So right from the beginning, we knew that this probably wasn't going to be as simple as our lovely, elegant model made it sound. So looking at the global sulfide database, there's an awful lot of data here, and I don't have time to go into it in depth, but doing statistical analysis based on the tectonic setting of the deposits that are hosting these minerals, basically we found that post-subduction porphyry copper deposit sulfides are statistically significantly enriched in bismuth, antimony, tellurium, and selenium. So that's good news. You know, they're all relatively chalcophile, so potentially that does support our model. But what about gold and palladium and platinum? Well, unfortunately, actually, in all the studies where they analysed for these metals, almost all of them were below detection limit in the sulfides analysed. And these are histograms from my own analyses, so from Maratra, Skouries, and El-Teniente, from the different sulfide types, showing palladium, platinum, and gold, showing what the concentrations were and how many analyses were below detection limit. And you can see that an awful lot of them were. And we were also able to do a mass balance calculation because I was able to, on the samples where I'd laser ablated the sulfides, I then crushed the same sample to do whole rock analysis. And we basically found out that actually you couldn't account for the concentrations of precious metals within the whole rock just with the concentrations that were in the sulfides. And this just means that gold, palladium, and platinum in these deposits must be hosted in accessory minerals. And it's not that unusual. So electrum is a very common accessory mineral in copper gold porphyry deposits and does host an awful lot of the gold ore in these systems. And as I said, in PGE enriched porphyry deposits, we commonly do identify platinum group minerals, normally palladium, bismuth tellurides within the hypogene ore. So this begs the question, how can you get a platinum group element forming if you don't have any palladium or platinum in your sulfides? And so it's been suggested that in porphyry copper deposits, particularly for electrum, that actually the gold was originally in the copper sulfides, and then as the copper sulfide cooled, the solubility of gold in chalcopyrite drops, and then it's expelled from the lattice to form the accessory minerals around the edge. But if that was the case, I would expect all of the chalcopyrites to be saturated with respect to gold for their crystallization temperature, which they're not. As I said, in almost all of the chalcopyrites I analysed were below detection limit gold and also below detection limit palladium and platinum. And so shameless plug here, if you're interested, we published a paper in 2018 where we suggested that actually we might be seeing instead a semi-metal melt. So in systems that have high bismuth and tellurium, experimental work has shown that in hydrothermal systems, actually an immiscible bismuth tellurium melt can partition from the hydrothermal fluid. And so what we suggested happened is that a bismuth tellurium, an immiscible semi-metal melt, a bismuth tellurium melt was formed, and it was carried as droplets, perhaps as compound droplets, in the hydrothermal fluids. And as it did so, it collected and scavenged palladium and platinum and maybe some gold from the surrounding fluid, concentrating it into these droplets. And then as the system cools, these precipitate as our platinum group minerals within the hydrothermal minerals. And we see textural evidence for that in Skouries, where there are droplet morphology, palladium, tellurium, bismuth minerals within euhedral hydrothermal quartz crystals, and also compound precious metal tellurium droplets, again, within hydrothermal minerals. So having gone to all that effort compiling sulfide databases, that's actually pretty useless when it comes to gold and palladium and platinum, and tellurium indeed, because they're commonly hosted in accessory minerals. So we need to turn to whole rock data. So these are box plots showing the concentration of various chalcophile elements in whole rock samples in El-Teniente, that's our subduction-related porphyry deposit in green. Maratra, that's our post-subduction PGE poor deposit in blue. And Skouries, our post-subduction PGE rich deposit in orange. So let's start with gold. Here, both Maratra and Skouries are statistically significantly enriched in gold above El-Teniente. So that does seem to support the Richards model that perhaps there is some tectonic control there. But whenever we look at the other chalcophile elements, particularly platinum, palladium, selenium, bismuth, and tellurium, we find that actually El-Teniente and Maratra are statistically very, very similar, have very similar concentrations of these, whereas Skouries is statistically significantly enriched. And so this, coupled with the fact that, as I said at the beginning, PGE porphyries are found in a whole range of tectonic settings, I think this can, unfortunately, perhaps rule out tectonic setting as the overriding control on palladium, platinum, and tellurium enrichment within porphyry copper deposits. So what instead could be controlling these? So looking at the whole rock data in a bit more detail, this is a Chalcophile element profile, including our PGEs, normalized to mantle for El Teniente, Maracdra, and Scurries, and then from the literature for PGE enriched porphyries and PGE poor porphyries, but these are all mineralized samples. And so you can see from the shape, first of all, they all have very similar shapes. We're not looking at wildly different profiles here. They all have a kick in cobalt. They're all mildly IPG depleted compared to PPGs. And the biggest difference in profile shape comes when you get to palladium, gold, and tellurium, where, for example, Scurries has significantly more palladium and tellurium than Maracdra, and Maracdra and Scurries both have more gold than El Teniente. And if I lay all of these over each other, again, you can see the shapes are very different, but our PGE enriched porphyries just have higher overall concentrations of chalcophile elements until you get to the palladium, gold, sort of tellurium bits of the profile, at which point we start seeing some differences. And the reason why I keep going on about tellurium is that a link has been drawn between tellurium and PGE enrichment in post-subduction settings. So this paper was published by Dave Holwell et al. In Nature Communications last year, and they suggested that there's a sort of transcrustal continuum in these post-subduction settings of mineral deposits, and that tellurium actually could be very important for transporting PGE. So one of the big problems we have in getting a PGE enriched porphyry deposit is how do you get your PGEs away from your sulfides in the base of the crust and all the way up to the top of the crust here, despite any sulfide saturation events that might have gone on in between. So what they propose, and what I'd sort of agree with, is that the residual sulfides from subduction are partially melted, and so the nickel and IPG probably stay down in the cumulates, but the gold, copper, and some of the palladium and platinum and the tellurium are melted and mobilized upwards in our source melt for our post-subduction porphyry. However, during this process, there are going to be various sulfide saturation events, and also as pressure drops, any sulfides which are entrained will be dissolved. And obviously palladium and platinum are relatively incompatible in a silicate melt. And so if you had enough tellurium present, you could form a semi-metal melt, which would carry the palladium and platinum in all the way up through this system, and then allow them to be deposited in your post-subduction porphyry deposit, as we see in Scurries, where we do see evidence of a semi-metal melt. And so we would like to suggest that actually, potentially, this could also happen in a subduction-related porphyry. So we know that there's tellurium in the mantle wedge, and actually seafloor sediments can be incredibly enriched in tellurium. And so I would sort of like to suggest that potentially there could be, in some subduction settings, enough tellurium to form an immiscible semi-metal melt again, because again, we still have the same problem here of even if all of the PG weren't partitioned into residual sulfides, how do you then get them up into the mid to upper crust in a felsic system to form a porphyry deposit? And so, yeah, I would like to suggest that potentially the residual sulfides are being formed, and yes, these are going to scavenge the majority of particularly the IPG, but if there's enough tellurium, potentially maybe a separate semi-metal melt might form. This might collect some of the palladium and platinum and potentially some of the gold, and again, be transported up through the crust, allowing the formation of a PG-enriched subduction-related porphyry copper deposit. Now, this is obviously all quite hypothetical at the moment and a bit of a whistle-stop tour. I unfortunately haven't had time to talk about, for example, hydrothermal deposition models, and also the role of alkalis, which could be very important. But I think that basically, I think that potentially, yes, gold could well be tectonically controlled. I think that, you know, the Jeremy Richards model probably does hold true for that, at least to a certain extent, but it doesn't hold true for PGE and tellurium. We see PGE enriched porphyries in lots of tectonic environments. However, they tend to be, all of the PGE tend to be in telluride minerals in hypogene ore without any remobilization having occurred. And I would suggest that actually maybe it's the availability of tellurium and other semi-metals to form these semi-metal melts that decides whether you're able to form a PG enriched porphyry or not. Now, I guess the caveat to that is actually we don't have very much data for tellurium concentration in porphyry deposits. In fact, the only whole rock data I've been able to find is ours from this study. So 3 porphyry deposits is probably not enough to stake an entire global model off. So I'm sort of moving on to more bushveldy research, certainly in the near future. So if anyone wants to pick up the baton on this and look a bit closer at that, that would be great. So I've probably whittled on enough about this. So thank you very much for listening. Hopefully this will be published in Economic Geology in the near future. But if anyone has any feedback or questions, I'd love to hear them. Please put them in the chat, or else do get in touch. Thank you.